So first we will go around the room and introduce ourselves. And we'll just go this way, and we'll wind up with Don Novotny, who will introduce our speaker. So Dick Strombotny.
I'm Jack Affey, retired from the University of Maryland and NASA Goddard.
And I'm Don Novotny, who will introduce the speaker, and from NIST, retired.
Sherry Stenbakken, retired from NIST.
I'm Marcel Stenbakken, retired from the Department of Health and Human Services.
Dave Blackburn, retired NIST.
George Shetland, retired Army Research Lab.
Dan Costanza, retired U.S. Army Corps of Engineers.
Joe Rosen, retired from Tel Aviv University.
Mike Lubatsky, also retired from the Denver Taylor Model Basin.
Harold Williams, not retired, Montgomery College Planetarium, and a few other things. And on the 15th of August, this group generally has some tour somewhere. It's not going to be here, it's going to be at the Planetarium at Montgomery College. And
Tacoma
we're
Park.
going to eat at Tacoma Park. And we're going to eat at Busboys and Poets before that at 11:30. And then at 1, we'll have a planetarium show, and we'll do everything from Starry Night to Layered Earth. Who knows, maybe I'll even show you Rodinia, but not as good as the talk we're going to have here, because he knows a lot more about this than I do. I know very little, but I will know more after I listen to him. So now I will be quiet.
Joe Avelies, NRL, retired. I never heard about Rodinia until this month.
Rupert Chappelle, Montgomery College. I heard about the supercontinents when I was about 10 years old by reading weird books by a fellow named Churchward.
Okay, Don, all yours.
Okay, well, I guess by now we've all heard of Rodinia. Basically, it's a supercontinent. It preceded Pangaea by a couple supercontinents anyway. It formed about 1 billion years ago. It's somewhat different than the other supercontinents that I presume was going to be part of the talk. Our speaker is Chao Liu, who received his PhD in geoscience from Yale University and is currently doing postdoctoral work with Bob Hazen at the Carnegie Institute of Science. So with that, let's welcome Chao.
Thank you. Thanks for the introduction. And thank you all for coming for this talk. Today I'm going to talk about the supercontinent Rodinia, which is formed about 900 million years ago. And I will focus on the geochemistry and mineralogy associated with this supercontinent. The map in the background is a reconstruction of Rodinia at about 900 million years ago. And you can see from this configuration that North America, Laurentian, is in the center of this supercontinent. It's surrounded by other continents such as North China, Siberia, etc. You recognize most of the continental pieces nowadays. So, what is the supercontinent cycle? So, in geologic history, the continent aggregate together and then drifted apart repeatedly, and the aggregation landmass is called a supercontinent, and this repeated process is called a supercontinent cycle. So the animation in the background is a little bit busy, but starting from 250, it's like, again, yeah, this is more than 250. This is Gondwanaland. This Gondwanaland break up, and then all the pieces just moving up. Again, Gondwanaland break up, and then it forms Pangaea at that time, and then Pangaea break up, and then all the pieces just drifted apart from the modern thing. One more time, Pangaea break up, and then everything goes back to the modern map. There's some studies saying that this today's configuration is not the final one. There will be another supercontinent around the North Pole, maybe in another 200 million years. So
Can't wait to see it.
200 million years, yes. So this is called supercontinent cycle. Start from Gondwanaland, form Pangaea, and then Pangaea break up. The next one is called, I think it's called some kind of amnesia. America and Asia come together. Anyway, so that's the supercontinent cycle. So what actually caused this supercontinent cycle? So the answer is plate tectonics. I will not go into the details of plate tectonics because it will take at least one semester, I think. So I will just briefly introduce the concept of the plate tectonics. So the Earth's surface, like this layer here, is called the solid Earth surface called the lithosphere. Is made up of rigid hard rock plates, several of them, and then it's beneath this rigid lithosphere, you have the viscous mantle. And also the Earth is trying to lose heat from the interior. One way to lose heat actually is through this convection of this viscous mantle. So when there is a convection in the mantle, along this convection path, the temperature actually decreases with this along this path. So you can notice that the lithosphere, I don't know if there's a stick or something. So the lithosphere is very thin at the very beginning, and then it actually becomes thicker along this path because the temperature drops. And then become thicker, and then it becomes denser also, because the thickness actually causes some phase transition of these minerals, and then it forms some dense minerals. So this part is actually thicker and dense. So it actually has some kind of gravitational drag on this thing, and also because of this force, and also because of this convection, the drag from this convection cell, so the plate actually moves in this way. So the continents are all on this plate, so it should actually drift together with this continent. That's how actually you saw this plate motion and the continent drift and everything. So the result of this process is that so because of this convection, so all the continents will be pushed into a spot around some spot where the convection motion is actually minimal. So it's stabilized there. So it formed a supercontinent. That's how it actually formed a supercontinent. But the thing is that the supercontinent will not stay at that spot forever because it acts as a thermal blanket. So actually some heat is building up beneath that supercontinent. So after maybe 100 or 200 million years, so the convection beneath that supercontinent actually restart again. So it breaks up the supercontinent, and then just it goes back to this, and then push back to another spot, and then just break up and everything. So that's why we have these supercontinent cycles. So that's how the mechanism works. So we talk about supercontinents. What are the evidence for the supercontinents? So there are so many of them. So here I will just list the three most important. I think the most key evidence, most important evidence for supercontinents. The first one is paleomag. So the paleomag is on the left, kind of here. So you can view the Earth as a big magnet. So the way it works is that as the magnetic minerals such as magnetite and sometimes even hematite, they actually aligned their alignment, their orientation of that crystal. When they are formed, they actually locks the information of the latitude when they are formed. So I would say for example, the magnetite formed at the South Pole will point up. The magnetite formed at the North Pole will point down. So that's how they actually from that, and also in the for example, in South America and also in Asia, actually the pointing of this crystal actually quite different. You can, based on that alignment, you can actually tell the latitude when these crystals are formed. And then we are talking about the single crystal, and when you analyze the hundreds of thousands of them from one area, you can actually tell what is the location of that area at some time. Maybe if the crystal formed like 100 million years ago, from the magnetic orientation, you can tell where is the continent through time. For example, this is, I think it's in the shape of India, maybe. So it's like through time, actually, maybe this is like 100 million years ago, 50, and then just present. So you can actually draw a path of this continent through time. And if two continent pieces have the same path at some time, that means they move together. That means that probably means that these two continents actually work together because they have the same path at that time. So that's actually one evidence for this, if two pieces work together at some time. The other evidence is actually from geochronology. The meaning of geochronology is that the age of different kind of rocks. For example, if you compare South America and Africa, they have two sets of rocks. The green one is Archean crust, and also the hairy one is actually Proterozoic mountain belts. So what geochronologists did is actually they date these rocks from this area, and they found that the same kind of rocks have the same age. So that means that they form at the same time at the two different continents, but they like for many different kind of rocks, they have the same same ages through time. That means Africa and South Australia were together. If they are not together, then it's very unlikely that they form exactly type of the rock at the exact same time. One thing I want to say about this geochronology is that zircon grains, which is shown here, the legend is 30 micrometers, is very important in this process, this dating process, because zircon is a mineral that is very robust. So it's very hard to destruct them. So once they are formed, they are there. Even though all the rocks are gone, the zircon is still, you can still find the remains of zircons, either in the sands or in the sedimentary rocks. So the good thing with zircon is that it's actually when they are formed, it takes all the uranium around it. So the zircon structure prefer uranium, and it doesn't want to have lead. So at the very beginning of the zircon formation, it takes uranium and no lead. And then what you can do is that you can just get a zircon grain and then measure the uranium to lead ratio, because uranium decays to lead through time. So we have a clock in this crystal, and then you can have the time. That's how actually you get the information of all these chunks on different continents, and then compare the age between them. The other interesting feature about zircon is that it's like the zircon grain number, the global zircon grain number is actually related to the magma volume where they are from. So if you have more magma formed, then you have more zircon, because zircon only came from magmatic magmas, granitic magmas. So every time when you see a peak of zircon numbers, that means that globally there is a huge global magnetic event. So that's the other thing with zircon that's super cool. So the third evidence is actually from fossils. So here you can actually compare 4 types of different fossils and check their spatial distribution. You can see that for some fossil is found both along this region, is along South America and Africa. For this one, you found that in Africa, India, Antarctica, and also Australia. And this one is Australia and everything. So by comparison all this fossil record, you can sort of get a way of how the supercontinent looked like back in time. Anyway, so we have the evidence now. Next thing is that, okay, I talk about these three key evidence from for the supercontinents. But each of them has their limitations. When we talk about fossils, I need to introduce this first, sorry. This is the geologic clock here, starting from 0 and then this way. Hadean, Archean, Proterozoic, Paleozoic, Mesozoic. So it's like, if it's 12 hours, then like human, I think the first human only appears like less than 1 second ago. So it's super short time compared to Earth's history. And the thing with fossil is that it only goes back to about 30 million years, Paleozoic. So it's about maybe 2 hours on this clock. So we are losing, we don't have any fossils going back. So it's quite limited. And also the paleomag. Paleomag, it works really well for like recent samples. It goes back to, I would say for a single crystal. For a single crystal, it's very reliable, goes back to 200 million years, less than 1 hour. But if you can always, for paleomag, you can always analyze a lot of them, like hundreds, thousands of crystals, and then get some kind of statistical orientation out of that. And then people actually push this paleomag back to maybe 1 billion years because of the statistical power. But still, it doesn't go back that much. But the thing with zircons, zircon is just so robust. So the first zircon actually appeared. This is the Earth's oldest crystal that's found by John Wiley from Australia. So the uranium lead age from that zircon is 4.4 billion years. It goes back all the way to here. So it's very close to the start of the Earth. So zircons are super important every time when you want to study very old stuff, you need to go to zircons first because they have the most, they log everything, not everything, they log the most information from the early Earth. Okay, talking about zircons. Here is the zircon distribution through time. The x-axis is time, y-axis is the zircon grain numbers. This is a compilation of detrital zircons. That means they are found in sediments or sands. So you can see that there is a pattern here for each, except for Pangaea, because Pangaea the cycle hasn't yet finished. It's going to be finished soon. For any supercontinent before Pangaea, so the peaks of zircons actually coincide with this assembly stage of the supercontinents. So when the continents are coming together, before they actually assemble together, so there are a lot of subduction collision going on. So along with the subduction zones, you have a lot of magma formed. When you have a lot of magma, you have a lot of zircons. So that's actually how you see all these zircon deposits. That means there are a lot of subduction tectonics going on during this supercontinent assembly. But think about zircon. Zircon is super important, but zircon is only a minor mineral in rocks. For example, granite is the most rock that is the rock type has the most zircon grains. But even from 100 specimen of granite, the major minerals you find is actually quartz, autoclase, albite, and biotite. You actually don't see zircons here. You have to grind it to a very fine scale and then use the microscope to find the zircons. So zircon is only a minor part of these rocks. So the question is that we know the distribution pattern of the zircons. How about the other minerals we have? So my advisor and my colleagues actually trying to study the temporal distribution of all minerals through time. So they actually end up with a mineral database. It's called. You can go to this website to find it. So in this database, there are like all of the mineral species you can find on this website. It has the structure. It has the chemistry and also the publication associated with where they are found and everything, all the information you can find. You need it. And also, one important thing that they have like one option to look at the age of this of all different kinds of minerals through time. So you can actually hit the evolution button, and then to look at this the age of different types of minerals. So this is actually a compilation of all high temperature minerals from that database. So by saying high temperature minerals, I mean minerals that formed in magmatic or metamorphic rocks, which has a very the age of them are very well constrained. So by looking at this diagram, you can see that so it seems that the peaks of this high temperature mineral are also like associated with supercontinent assembly. You see peaks here, here, and here. But the thing with this mineral database is that zircon is not, I would say all of them are not as robust as zircon. So you see a lot of like these minerals in the recent time, and you see less of them in the past because these minerals don't like last as long as zircons. But if you zoom in to the old time, by old time I mean Precambrian, before the fossil record, you can clearly say that associated with each supercontinent you have peaks. This is Gondwana, this is Rodinia, this is Newland, this is Carnegie. For the 4 supercontinents you have a peak. But the thing is that with Rodinia, the peak is kind of, I would say it's not extremely small, but it's kind of fewer compared to other supercontinents. And then I can just look at the based on the mineral composition. You can actually look at the subsets of these minerals. The thing is that this is for nickel. You see you are lacking a lot of nickel minerals. Cobalt also the same. Gold, which is super interesting, and also sulfur. It's like for most of the mineral you see, the Rodinia has like you don't say the record. You don't say in the record. You don't say these minerals. But I was thinking, oh, maybe that's the case for all kinds of minerals, but that's not the case. If you look at niobium and yttrium minerals, you see, the peak is super high. It's for niobium is almost close to the most abundant time to form niobium minerals in history. So you can actually compile this result on a single plot, and you can see that niobium, yttrium. So this is the elements of the minerals, and this is the percentage of Rodinia mineral. So it says the percentage of mineral formed during Rodinia compared to other supercontinents. So the line here is actually the zircon percentage. Remember, the zircon has a peak also during Rodinia. So you can see that for niobium, yttrium is super high. It's even higher than zirconium, the zircon peaks. But in the other end, you have like gold, platinum, nickel, and all the expensive things are actually missing. So it's just. So we have 2 questions here. The first one is that, so why is the formation of high temperature niobium, yttrium minerals as pronounced as, or even more prominent as zircons during Rodinia assembly. So the second science question is that why are many other minerals, especially nickel, cobalt, PGE, gold, all these expensive stuff are actually missing during Rodinia assembly.
What is PGE?
PGE is platinum group elements. It's platinum, rhenium, palladium,
Okay.
so all those like
Yeah.
very expensive stuff. You don't say them.
There are lots of very expensive.
Yeah, they are very expensive. I would
Thank
say.
you.
That's with one single mineral database, to answer this question is just very difficult because that's the single information we have. So my approach actually goes back to geochemistry, goes back to the geochemical database we have. Because geochemistry of different rocks gives, first of all, it gives to form a mineral, you need to have some background concentration of this element. So it gives what is the source material for the minerals are like at that time. The second advantage of geochemistry is that using specific tracers in geochemical database, you can actually tell what is the tectonic setting to actually these rocks are formed, and then to tell at what kind of environment these minerals can be formed. So that's why I goes to geochemical database. So the geochemical database has been built since, I think goes back to 2001. It has been 18 years. So Kirsten Leonard is the one who is in charge of this database. So this database is actually a database compiling all the geochemical data that has been published. So right now, I think there are at least more than 4 or 5 million data points in that database. I mean, compared to biology, compared to people works in medical business, it's still a small database. Because those people are dealing with maybe billions of data, but right now for millions of data is super big. Actually, for geology, this is very big.
It looks like the Atlantic Ridge zone, the Mid-Atlantic Ridge, is very well studied.
Yes, there is a sampling bias for sure, because people goes to, America has a lot of data points, also Europe. Maybe around this Andes Belt, in East Africa Rift, because these are interesting areas. People tend to get numbers from those things. Remember, always keep in mind there is a sampling bias in this database. Anyway, so talking about sampling database. So the way because you just said there is a sampling database, so actually you can not just get the data and then just plot everything based on that data. You need to resample because of the sampling bias. So the approach I am using is actually, so this is the equation. It's kind of simple. It's a very simple equation. So what is this equation does is that actually it calculates a weight for each sample. So if the sample comes from an area that has a lot of things has been sampled, it will get a smaller weight. If a sample comes from someplace, for example, Antarctica, because there are so few samples of them, they will be assigned to a much higher weight. And also there is a time component here. It's like because we have more recent numbers and less Asian more recent samples and fewer Asian samples. I'm sorry.
If T is time, what is Z?
Z is actually the longitude and latitude coordinates.
Okay.
Yeah.
Right,
So you calculate the spatial. This is actually the distance between any two sample location.
Right.
And this is the age difference between any two samples. So Yeah, that's what it does. So I did this. I would say this is it's a very simple equation, but it's a very time-consuming computation problem because it's like it takes like 3 or 4 days to finish this on this laptop. So yeah, so I did the resampling, and also the other thing is just basic statistics. Just get this mean, median, quantile, confidence intervals, everything. So the way I point this out because people see geology as a quasi-science in some way because people think what geology does is not quantitative enough. So they think there are a lot of biased data. They say geology is not as quantitative as other science. So what I put this on here to say that what I did here is actually has some statistical power. It has some quantitative component in this study. So that's why I want to point this out.
Actually, it's going to be very powerful.
Yeah. So this is the result from the geochemical database. This is the niobium concentration. Niobium. Remember niobium? We have a mineral peak at that time during Rodinia. So this is the niobium concentration through time. So the ppm means part per million. It's like 10 to the minus 6. So you can say that for both median and mean, all the statistics you have at Rodinia, or maybe a little bit before Rodinia, you have a very high peak at that time. So this actually agree with the mineral peak. So that means at that time the source rock is enriched in niobium. So it actually provided more niobium to form minerals. So this is niobium. So this is yttrium. Remember? Oh, I'm sorry. Yeah. So this is yttrium. So remember, yttrium also has a high peak, the mineral peak. So when you do this to geochemistry, this is Rodinia, and also you see the peaks for yttrium. So the story is the same for niobium. Is that the rocks formed at that time has a high background concentration, and then because there are more of them, there's more source material than the minerals just formed because of that. So also I want to say zirconium, because zircon, remember zircon peak is also very high. Zirconium follows the same trend. Statistically, it's very high concentration at during Rodinia assembly. And okay, these are very nice pictures, but some people will say a lot of people again comes back to the criticism we have. It's like geologists are not quantitative enough. So if you want some numbers, I give you some numbers. So here are the numbers, but you don't want to go into the details of this. So this is actually comparing Rodinia to other different kinds of supercontinents. So what I do here, I do a very basic two-sample T test. Is that every time you see a T statistic bigger than 0, that means that Rodinia is, the concentration from Rodinia is higher than other supercontinents. Also, I did that for both mafic and felsic rocks. By mafic, I mean the silica concentration is lower, it's around 40%, 40 to 50. By felsic, I mean it's high silica rocks. I do this because of this all the geologic thing, because there are two types of rocks that are very abundant on the Earth. One type is mafic. It's more like the basalt. If you're familiar with Hawaii, those are basaltic lavas. Yeah, those are basalts. The felsic one is more like granite. So these are the most common type of rocks. So I took them out and then to compare them like basalt to basalt, granite to granite. So you don't want to compare apple to oranges. That's why I did this. So the take-home message is that t is bigger than 0 for most of them, and p is less than 0.1 for most of them. That means this statistically the result is very significant. That means these peaks we saw at those figures are actually true. It's not like false stuff. So as I said before, that the beauty of geochemistry is that not only you get some background information, background concentration in the rocks, you also can get the tectonic settings out of these tracers, because each element is actually during different tectonic process. They actually either they are enriched or depleted at different settings. So this is I think it's almost 40 years old diagram I use. People use this to distinguish different kind of rocks for like 40 years now. So what I put here is that this is the mafic rocks. As I said, this is basaltic stuff, basalt. This is the felsic one, granite. So the green one is Rodinia. This green thing is Gondwanaland, and also this blue cross is Nuna. So the thing is that when you compare these three supercontinents, you can see that this is Rodinia here, Gondwanaland, and Nuna. Rodinia, Gondwanaland, and Nuna. That means that for both mafic and felsic rocks, the tectonics of these rocks means that they are formed during some kind of within plate magmatism, instead of for other supercontinents more like arc collisional tectonics. So hold it for a second. This explains why, and this explains why. So within plate, I mean like within very stable continents, or within a very stable plate. One example for within magmatism is from the East African rift. Nowadays, it's intraplate, and also for Hawaii, it's also intraplate. This is a Hawaii style thing. By arc collisional, I mean that there is a subduction zone. It's more like the Andes, the Rocky Mountain is arc collisional, and also Japan is also arc collisional, because you have a lot of subduction going on. This is more like Japan style here. So the thing is arc collisional, like Japan, like Rockies. Like when you form a rock from this kind of area, is that the magma actually goes through this layer here. This layer is called depleted mantle. So when the magma goes through this, it actually interacts with this mantle. So the niobium, yttrium, zirconium, all these elements actually got sucked up in this. So all the magma you have at the surface actually quite depleted in this kind of these three elements. But for intraplate magmatism like East Africa and Hawaii, so this actually the magma actually dries up very quickly. You don't react with this lithosphere very much. So you have high concentrations of niobium and yttrium and zirconium. So that's actually why you see the high peaks of these three elements during Rodinia assembly, because it means that at that time you have a lot of rifting going on when it's formed. And then go back to the mineral locations we have. So there are three colors I use here. So the blue color is the intraplate settings, where you have a lot of like East African style rift going on. This is a very famous one. It's called, it starts all the way from northwest Canada and goes to, it's like radiating from Canada to US to Greenland, and then to, I think that's Siberia. So it's a very huge intraplate mechanism going on at that time. And this is all the blue dots means, and also the green dots actually collisional style. It's more like, this is more like the rocky style subduction. You can see that there are only like a handful of the green thing on this plot we have, which is quite weird. And also we also have some red stuff here. This is a Greenville Rodinia. The thing with Greenville is that here all the dots I plot is red. It's not in green because the minerals I found in those spots, even though they are close to the subduction zone, but they only formed after the subduction. So it's the subduction stopped, and then it has some kind of extension going. So the collisional force is released, and then there is a destruction of the orogenic belt, and then those red stuff formed. It's not found during the collisional, but it found in extensional tectonic settings. It's a little bit different. So more about intraplate mechanism. So there are some rock evidence for this during Rodinia assembly. You can find a lot of massive anorthosite. Oh, by the way, anorthosite is a very interesting type of rock. On the Earth, you only found those rocks at that time during the Middle Age of the Earth. And the other place you can find anorthosite is actually on the Moon. It's like on the Earth, you only found that during Rodinia, not other time. You can have some of them, like maybe occasionally here and there, but there are a lot of them during Rodinia assembly. Some people say, okay, maybe it's comparable to the Moon, but I'm not sure about that. And also there are some A-type granite. So I will not go into the details of that because there are different kinds of granites you have. And also one specific interesting rock is called NYF-rich pegmatite. These are, by the name you can see that it's enriched in niobium, yttrium, and fluorine. So these pegmatites are very interesting because it contains very high concentration of niobium and yttrium, and then because of the high concentration, you form these niobium yttrium minerals, and that's why you have these mineral peaks at that time. And so this is a pretty, I would say, not very beautiful rock from Colorado. This is one type of this kind of pegmatite. You can actually find this. I think this is columbite, and also the yellow one is this uranal stuff. So it's a very ugly piece of rock, but it contains very rare minerals, which makes them maybe beautiful in some way, I think. So I think we have the answer. Right now we have the answer for this part, why these niobium yttrium minerals are enriched during Rodinia. So the other thing we need to address is that you're losing a lot of them at the other end of the spectrum. So I went back to the geochemistry database, and because nickel and cobalt are missing, so I tried to get gold and PGE concentration, but so the numbers are not very, we have only less than 1,000 samples in the database because they are very hard to measure in the lab. So we cannot get any statistically significant result for gold and PGE. So I only plotted nickel and cobalt here. So the thing with nickel and cobalt is that you don't see anything different during Rodinia. We are expecting maybe, because the minerals are missing, maybe the concentration is low, but no, it's not the case at all. You don't see anything like missing. So the implication is that maybe maybe these kind of minerals were not formed because of the environment at that time is different, or maybe they are actually formed, but they are just eroded away. It's called preservational bias. So let's look at them, each of them specifically. The first one I want to mention is that so this missing mineral scenario is actually consistent with previous studies of all deposits. For this figure here shows the distribution of all deposits through time. We have VMS, we have porphyry, copper, gold, and gold and silver, gold and lead, zinc, and everything. So you can see that at 1.0 billion years, you just don't see them. These all deposits are very rare. So the other thing I want to mention that all these types of all deposits, they are this is a very basic figure. But one thing to just the take-home message is that all these types of all deposits actually form in this kind of environment. You have subduction, you have volcanic arc, and then on the surface of this arc, you form all these kind of all deposits. But they are just missing at that time. So remember, I mentioned there are two hypotheses. One is that the environment is not good enough to form these minerals. So just one hypothesis is that by large, as of 2017, they try to explain why you don't find all those ores at that time. So what he is trying to propose is that at that time the FO2 of the atmosphere is very high. So actually the fluids, all fluids actually become oxidized. When you have oxidized all fluids, you cannot form those all deposits. But that's what he proposed. But if we go back to the atmospheric O2 through time, so this is the time we are talking about. I don't see anything like very high at that time, because like recently it's like this. And also, according to this diagram, so if this means FO2 of this time is high, it means this time, and this is where Nuna is here at 2.0. It's comparable. It has comparable FO2, but I don't see anything missing from Nuna. So I think that this generational hypothesis is just not valid because of what we saw here and here. It just contradicts to each other. I'm more leaning towards to the lack of collisional settings because that's what you see on the map. As I said, the green dots are just, you don't have a lot of them. You only have like 4 or 5 points here. But compared to intraplace, it's just nothing. So we're missing a lot of them. So I'm leaning towards to the erosion hypothesis, so which is not new at all because previous studies suggest that Rodinia is assembled in an extrovert assembly. So this is a thing that geologists always try to do, to use a sketch to propose some hypothesis. So this is actually, so when you form a supercontinent, so what they propose is that there are 2 ways to form a supercontinent. One thing is that the previous one break up, and then somehow it goes back together in the same configuration or very similar configuration. So in this process, actually, most of the things formed along here actually preserved because it doesn't travel far away and then just come back. And it just didn't travel so much. The other way is actually inside out. So in this way, so the outside of the supercontinent actually rotated away from its original position. Sometimes it travels all across the globe and then meet again to form some, like the outside of this original supercontinent meets there. So in this process, because it travels because it travels so much distance, so there are a lot of erosion of this of the thin film at that time. So a lot of people are actually saying that because Rodinia is formed by extroversion, these arc fins are just not preserved due to this process. So the other evidence actually, so when you look at this Rodinia origin, the origin means the collisional belt at that time. The most major Rodinia mountain belts is actually Greenville here in the US and also in Baltica. You can see that for Greenville, you have like multiple phases, like multiple collisional events going on. You have a early one, a later one, and also there are 4 phases. And these are all collisional, which means that the 2 plates actually pushing against together. But during these periods, you also have some kind of intervals that there's no collision going on. Just, it's pauses and it stops and then it's just extension. So these people, these studies actually propose that during these intervals, a lot of things actually eroded away because, when you release the pressure, everything becomes very easier to weather, so they just go away with time. So this is actually, there's a recent paper coming out soon in geology talking about this thing, and also they found a lot of, because it's very hard to demonstrate something is actually eroded away, they're just missing. They actually found evidence that there are a lot of sediments eroded from these mountain belts. They are actually found in West Africa and also in Midwest US. So I think this one has a very promising future. So and when you go back to this, also the erosion also consistent with the geochemistry, geochemical data, because with what we saw here is actually there are a lot of intraplate things preserved for Rodinia. The way to look at this is because maybe it was similar to Newland and Gondwana in this part, but because the erosion of this part, so the geometric mean just shifted to the intraplate. So I think that's all the pieces actually agree with each other. So I'm almost finished. So remember that I asked 2 questions at the front of this talk. Is that why is the formation of this Niobium yttrium minerals actually pronounced at that time? So the answer is that because the tectonic setting is quite unique, you have prevalence of intraplate magmatism. The other question is why are the other minerals actually missing? So I'm leaning towards to the interpretation that there's a poor preservation at that time. So the implication of this study is that, so people always say that 1.7 to 0.7 billion years of the Earth is called bottom billion because nothing actually happened at that time. But based on this study, so a lot of things actually happened. It's just people don't look at the data very carefully before. The second thing is that at that time, the tectonics is quite different at that time. It has prolonged asteroid assembly from a second continental crust and via two-sided subduction. These are just geologic jargons. Just remember it has a different type of tectonics at that time. So for the future studies, all I present here is actually data, observational data. So it's worth trying geodynamic modeling to model how the continents actually moved at that time. And also, I'm talking about this tectonics and everything, because the Earth system is actually interconnected. So everything interesting happened to the rocks. It should have an impact on the climate. So maybe it should be investigated if there's any influence on the climate. Why I said that, because when you look at the time, so this is Rodinia right here, and then it break up right here, maybe here. Yeah, to mount there. I would say for this one is people say there's a snowballs, but it's not that solid. You don't have much evidence for that. You have only 1 or 2 sample location for this story. But for that snowballs, you have global record, and that one is very
Core
robust.
samples?
Yeah.
Do they have core samples?
Not going back that far.
No, maybe not that far.
Core samples?
No ice.
No ice.
All right.
No. Ice core goes back to only, I think the maybe 100,000 years. That's all you have. You cannot go back to 1 million years. So 1 million years on this is like nothing. Yeah.
I think ice cores go back about 400,000 years.
400,000 years.
Yeah.
Okay. Yeah.
From Antarctica.
But the minerals last much longer.
Yeah.
Yeah, but
Yes.
a lot of minerals actually lost. Only zircons goes back to the very early stage of the
Did
Earth.
the atmosphere getting oxygen affect any of that geochemistry that you were showing us?
Not really, because I'm talking about the magma from deep in the Earth, right? So the oxygen will affect the surface of the Earth.
Right,
It's
okay.
different.
Iron.
Iron?
Iron,
Yeah, iron. I mean.
well, that's evidence. You have to oxidize the iron first.
Yes.
That's right.
Yeah. Yeah. But I'm looking at magmas. I would say for the mantle, because they are sort of coming from the mantle. Mantle is huge compared to the surface, so it's very hard to oxidize the whole mantle.
I
So-
have a question that I thought of early in your talk.
Yeah.
And that is, when you were showing the different supercontinents.
Yes.
Is the area of the crust about the same?
No.
Or does that vary
it's
widely
for the-
too?
If we compare everything, like after 1.8, I would say the area is very similar, because the continental growth is finished about. A lot of the continents actually grow by 1.8. So you have a lot of newly formed continents at that time. But after that, it's debated, but you don't have much new.
You don't really have a map, okay.
I don't have a map, but you can. This is the beauty of zircon. Based on zircon different isotope measurements, you can actually tell the story of how much continents actually formed. So people show that based on zircon, again, like before 1.7, most of the continents actually formed. So after that, it's more like you form new pieces and then you just eliminate some old pieces. So the total volume of the continents is about the same, I would say. Yeah.
Oh, it's the volume that is conserved.
Yes. I'm sorry.
Yeah, when I worked at NASA,
Yeah.
I worked with the magnetic field models, and
Oh, okay. Yeah.
and, the Earth's magnetic field has changed
Through time, yes. for
over
sure.
time. So,
Yes.
in the early part of your talk, when you were talking about identifying where
Yeah,
where these minerals came from
Yeah.
by looking at the orientation of the
Yeah.
magnetic field, you have to evolve your magnetic
Yes,
field
yes,
model.
you-
So you're looking at the
Yes.
magnetic field model for that era.
You do have for the magnetic field thing, they have a reference thing. Every time they compare, they keep that in mind already when they do all the calculations. So the magnetic field always like reverse through time. So they have a bar to check that if it's
Yeah,
reverse or
but not just reverse, but it's not just a dipole. There are quadrupole and octupole, and the
Yes, quadrupole is a huge.
well,
Yeah, it's a
the
huge
dipole
problem.
is a big
Yes.
one, but
Yeah.
and the position of the pole has moved with time.
Yeah.
The magnetic pole.
They call it true polar wonder. We call it the shift of the magnetic pole. So the thing with paleomag is that what they do is actually they analyze thousands of different crystals from several different continents, and then they compare all the continents. And if the pole of each continent actually don't agree with each other, they actually do some corrections. And then in the end, So they actually can give some information of how the pole actually shifted through time.
You have to compare the,
Yes, yeah.
the rocks from different ages with the magnetic
Yes,
field.
yes. You need to
from-
have very well age constraint, and also you need to have very well paleomag data to do this kind of stuff. It's very hard, I would say.
Yeah.
Sounds very difficult.
It's difficult. It's just a lot of work. I mean, the logic is simple, but if you want to, I know there is one professor at Yale, David Evans, doing this kind of reconstruction back to 1.7, 1.8 billion years. It's just super difficult, I would say. First of all, you don't have a lot of sample at that time. Second of all, you need to make a lot of assumptions, and also the lab is super expensive. You need to shield all the geomagnetic field. You're working, I would say, it has a big metal box. We work in that box.
You said that things like yttrium, niobium are enhanced at these hot spots. Does this mean a place like Yellowstone is more enriched in those elements?
Yellowstone is quite different. Yellowstone, even though it's very close to the, even though geographically is quite far, but it's very close to the rocky, like the Andes Mountain. Okay. So it has a relation to that subduction belt. Okay. When talking about hotspots, it's more like Hawaii style. Yeah. Also East African, the rift, a big rift. There's nothing close by. There's nothing subduction. There's no mountain belts, so it's more like Hawaii, East African stuff.
What is the word Rodinia? What does it mean? Where does it come from?
Rodinia.
Like
Yeah, I got that same
all
question. Yeah.
Land?
So it's come from Russian. It means give birth to, I think. So the meaning of Rodinia means that after Rodinia, you have everything, like all the you have actually multicellular life after Rodinia, but before Rodinia you don't have that. So it means give birth to life forms, I think.
Now you have the two snowballers, but I understand it's also the hothouse Earth where the carbon dioxide goes crazy.
Yeah.
Where are those? Is that occurring around the same time? You're alternating 750 to 635 million years ago between hothouse Earths and snowball Earths?
So first of all, at that time there are two snowball Earths. So the hothouse actually is not a thing because every time we have CO2 in the atmosphere is going to be greenhouse, a hothouse climate. Second of all, the snowball Earth, after snowball Earth, in order to defreeze the Earth, you need to have build up CO2 in the atmosphere. So every time you have a snowball Earth, then there is deglaciation. Then it's followed by hothouse environment. Does that answer your question? Or what is your question? I'm sorry.
Well, I'm only basing what I've read and
I
know very little about it.
It's CO2.
Don't the
Everything is CO2
volcanoes
controlled.
erupt and put the CO2 in the atmosphere?
Yes. That's
and
how
that
you
warms
build
the
up.
planet?
You build up, and then you warm the. Actually, that's my PhD thesis. So yeah.
With regard to the name Rodinia here, this is from Wikipedia, and it says it's from Russia, meaning to beget, to give birth, or possibly another word meaning motherland, birthplace.
Ah, okay.
So
Yeah, that was about right.
If you've completed your talk, we want to thank you.
Great. Yeah, I think I completed. Thank you very much. Sorry, I try to be as clear as possible, but sometimes still get into.
No, you can't tell us everything you know in 1 hour.
I'm trying to avoid all the geology jargons, but it's very difficult to do a talk without those jargons, actually.
Yeah.
Well, I think we all have learned a great deal.
Thank you. Hopefully.
Thank you.
From your talk.
Ask me about the magnetic field models. Basically, they decompose into spherical harmonics and then do a time evolution for each harmonic. And then you put them back together again at the later time.
Yeah, I would say my advisor, Robert Hazen, would give a much better talk than me,
Yeah.
because he knows his audience very well. He's a very
He spoke to us about 4 or 5 years ago.
yeah, he's a very good.
Yeah, and there was a,
We'll be asking him to speak again, though.
Yeah.
and he's
About the Carbon Observatory.
Yeah.
and computer. There is a NOVA that these things get rebroadcasted a couple of weeks ago called Life's Rocky Start, which is primarily a lecture and interviews with Robert Hazen about how the geology and the biology co-evolved in the Earth.
But I think one
there he
thing,
is.
one thing with all this work is that we're talking about geology, we are dealing with very ancient samples. So the problem is that you don't have a lot of them. So if you go back through time, so the error bar becomes bigger and bigger. So the story I'm telling here, I would say I have confidence in it, but it's not 100%. There is always some error bar associated with this story because it's 1 billion years old. That's my thinking.
Are there any other questions?
How did you become interested in this?
This?
Were you like when you were a kid? Did you read about plate tectonics? Or?
I came originally from China, from a very poor family. I don't have a lot. We don't even have a television at that time when I was young. So all I have is actually the radio. So there is some kind of pop science radio show talking about dinosaurs. Use some also like continental drift. So they're comparing the dinosaur fossils on Africa and South America. I think that's super cool. So that's how I got started. But it's almost like 25 years ago.
The fossil evidence.
Yeah, fossil evidence.
Of,
Yes. Yes.
The places that are now separated were once joined.
Yeah, I studied Nova Earth for my PhD, so I thought it's a very cool project. And then, I moved 100 million years earlier to study Rodinia. So I think it's all kind of, it's a destiny, I would say.
I worked with a man named Liu.
Oh, okay.
As he was I was his contractor officer.
Okay.
It's a very widespread Chinese family.
Yeah. I would say there are at least 20 million people with the same family name.
With the name Liu.
Yes, 20 million. So there are a lot.
Yeah, I work with Chuansheng Liu in the physics department at the University
It's
of
a
Bradford.
very common.
Yeah.
It's like Smith.
Yeah.
Yeah, well, once again, thank you very much.
Thank you so much. Thank you.
Don, did you ask him about?